Hi, students. This lecture is over chapter 22 on magnetism. I'm sorry, chapter 21. 21 on magnetism. Actually, it's chapter 22 in OpenStax. So I was looking at 22. So we're going to be out of alignment with OpenStax for a little bit. Again, OpenStax, what's in chapter 20 in our book, Cutnell and Johnson, actually was covered in chapters 20 and 21 in OpenStax, the whole concept of electrical circuits, resistance, and the other topics. So OpenStax then starts with chapter 22 and magnetism. We're going to be on chapter 21. So not to confuse, a lot of the OpenStax problems I'm going to work out are going to be chapter 22 problems of OpenStax. All right, so we're going to be a little bit out of alignment between OpenStax chapters and the Cutnell and Johnson chapters for a few chapters. We'll line up again around optics. All right, so anyway, magnetism. So when we're talking about our study, I've been saying we're studying electromagnetic theory, and indeed that's true. But initially, it was thought that these were different fields of physics. The electricity was one area of physics, and separately, magnetism was another area of physics, and the two did not have anything to do with each other. When we study it more closely, and in fact, we're going to start seeing this very, very soon here, is that as you progress in your studies, and we'll start seeing this in this very chapter, and definitely in chapter 22 and 23, and 22 and 24 for sure in your book, you're going to definitely see that there is indeed a very intimate interplay between electricity and magnetism. And in fact, we will find that they are two aspects of the same electromagnetic field. But for right now, we're going to look at magnetic behavior and just think about magnetism. We're going to kind of leave electricity, where we had it, and we're going to go into magnetism. So we've understood magnets for a long time, even since the ancient Greeks. We've known about magnets for a while, and again, you've played with magnets as a child. Every child has. And so the thing about magnets is that you look at the very concept of magnets. What are they? They're you have a bar magnet, refrigerator. Well, first of all magnets attract iron. So it's a chemical, an element, iron. I think it's element 26 in the periodic table. All elements attract iron. So be a magnet, you attract iron. Okay. Now magnets are characterized by two poles. A north pole and a south pole. So you draw yourself a bar magnet. In the simplest sense, you would just draw, here's your bar magnet, and it would have a north pole and a south pole. You find out that like poles repel, and unlike poles attract. If I take two bar magnets and put them next to one another, I'll have, again, this is just something, playing around with magnets, we discover these things, and we're starting at the roots again of another area of physics. And so we notice if I were to take two poles together, it could be north and the north together, or it could be the south with the south. We'll find out that this scenario where the like poles are right next to each other, they will repel one another. So this is going to be repulsion, repulsive force. There will be a force of repulsion in each case. Again, these are different cases. We'll put a little jagged line there. If I have enough space, we have a situation where we have attraction. So let's say I have a south and a north, and another south and a north. Well, here we would actually form an attractive force. Right. So unlike poles, north and south, attract. Like poles, north with north or south with south, repel. Okay, so the magnets have two poles. They can either attract or repel one another. All right. And so now with a magnet, what's different here is, okay, so when we talk about electricity, some of this looks familiar with electricity. You say like charges repel and unlike charges attract. The difference here with magnets is that you can't just get a north pole by itself. All right, so if I were to take a magnet, in order to say cut it in half, okay, you know what? I'm gonna extract the north pole and the south pole. So I have this magnet, and I'm gonna cut it in half. There's a north and a south, and I'm gonna take this magnet, I'm gonna cut it in half. What ends up happening is I end up creating two magnets that both have a north and south pole. I can dissect the magnet as much as I possibly want. I can get it all the way down to the atomic size. I cannot separate the poles. So at a minimum, we have a magnetic dipole. Okay, we talked about dipoles in one of the previous labs. You know, we talked about the electric dipole. Remember the electric dipole? That's formed by having, say, a positive charge Q in close association with a negative charge Q, and they have a distance S or a vector S between them. We said, well, the electric dipole moment was QS. Electric dipole moment was indeed a vector. Well, we at a minimum have a magnetic dipole. There is no such thing as a magnetic monopole. You cannot get a magnetic pole by itself. That would be a monopole. That is impossible. No one has ever been able to do it. An electric monopole is just a charge. So a charge is an electric monopole. So you can definitely have an electric monopole. You can have a charge all by itself. So I can separate out of this dipole, I can separate a positive charge and a negative charge, no problem. So electricity, the big difference is in electricity, you can have an electric monopole and an electric dipole and quadrupole and octupole and so on and so forth. But in magnetism, the minimum you can have as far as a magnetic distribution is concerned is a dipole. Again, magnetic monopoles do not exist. Okay, so now what happens inside of a magnet? What makes something magnetic, for instance? So we have some magnets that are naturally occurring. We refer to those as ferromagnets. So some magnets, this is how they were discovered initially. You know, we didn't make magnets. I mean, they were discovered. So magnets that are natural, so ferromagnets are naturally occurring magnets. Ferro is Latin for iron, which I believe is ferrum. In fact, you look at the chemical element for iron, what is it? It's Fe. You might say, why isn't it IR? You know, it's iron, right? Well, it's Fe because it takes the Latin name ferrum. All right, so something that's ferromagnetic, you know, so a ferromagnetic material is basically a ferromagnetic material is one that has natural magnetism. So ferromagnetic materials are naturally magnetic. All right, and so now they can be made into permanent magnets. And so, for instance, what are you know, some elements that are ferromagnetic by definition? Well, you know, we would, so for instance, certain materials automatically exhibit ferromagnetism. So clearly iron would be one of them. So what are some ferromagnetic materials? What are some natural materials you might expect? Well, clearly iron, cobalt, nickel. I mean, all of these are either naturally ferromagnetic or they can be made ferromagnetic. There's an alloy. We have one that's a rare earth alloy, or rare earth element called neodymium. That's another one that is oftentimes can be made ferromagnetic. All right, and so now, what causes something to be ferromagnetic? So I'm going to show you a little picture here right now. So let me share my screen. It's a picture out of the OpenStax textbook. All right, so in this picture, you know, generally speaking, a non-magnetic material is going to have these magnetic dipoles randomly oriented. So if you take a look at this leftmost picture, you'll see that the material is in little sections called domains. In a domain, there is a overall magnetic moment, an overall alignment of these magnetic moments, as it's called. But they're randomly aligned. And so given all these magnetic moments, statistically, they're all going to basically cancel out when they're randomly oriented. Now, let's say we put a very strong magnet nearby. Well, what's going to happen is we align it with a magnet. So in this particular case, we'll say we'll have a magnet that's really looks like the North Pole is at the back, is at the bottom. So the magnet is aligned, and I'll redraw this a little bit here. You can imagine there at the middle square, you can imagine there'd be a big, strong magnet where the North Pole is closest to the square and the South Pole is further away, and they're aligned. What's happening is the domains are going to get bigger at the expense of other domains. And essentially the domains that'll be favored will be the ones that'll align with the external magnet. And if you allow enough time to go by, you may have in magnetism where the entire material is magnetized along with the external magnetic field that's brought near it. And so if enough time, the magnetic material may look like the very rightmost picture, whereas magnetism is the same as that of the external magnetic field. So what we just got done showing here are these domains. So what I'm showing you is initially you have these random domains. Now, these little arrows are what are called magnetic moments. And we'll speak more about them, but the magnetization is characterized by a vector quantity called a magnetic moment. So in an unmagnetized object, so in an unmagnetized material or a non-magnetized material, the material can be divided into regions, can be divided into very small regions called domains. Each of which is characterized by an overall magnetic moment vector. Okay, that was that leftmost picture that I showed you. All right, and so we saw this, they're randomly oriented. It's an unmagnetized material and it's randomly oriented. So I'll try to do my best here to draw this, but again, what you kind of saw was very little breakouts of, regions, and, just they're all broken out. Again, I'm just kind of doing my best here to break this picture relatively quickly, but they're just broken out into random regions. And, again, I'm making them bigger than they really are just to kind of save time here. But again, they're just randomly broken out. And they're small and they're randomly oriented. And so you might have a moment here, moment there. They're all just completely at random. And overall, they should all average out to be about 0. So on and so forth, right? You get the picture. So the random magnetic moments in an unmagnetized object unmagnetized material sum to 0 statistically over many of these domains. Now, if I were to then take a very strong magnet and put it underneath the material, what will happen here is that the magnetic moments, or the arrows, are going to want to align with the magnet. So let's just say I have a big, strong magnet. I have a B field, a magnetic field, strong B field going this way. So it's some big, strong magnet, north, south, and it's creating this huge B field. What's going to happen is they're going to want, and again, a B is the letter used for magnetic field. So again, this is a magnetic field. The official letter we use is, well, capital B for whatever reason. Call it the B field. So what's going to do is it's going to want these randomly oriented magnetic moments are going to want to align, and of course certain domains are going to die at the expense of bigger domains. So you'll see the domains getting bigger, and the domains are going to favor, they're getting bigger, and they're going to want to favor alignment with, you might have one that's still out of whack, but in general, they're going to want to favor alignment with the magnetic field, the external B field. And eventually, if you allow this to go long enough, all these domains will disappear. You have one single magnetized object. So if you wait long enough, then these domains, I mean, certainly, again, some of these domains died at the expense of the growth of other domains. You wait long enough, what happens is all these domains, they all become one super domain. And that super domain is going to just all have one single characteristic magnetization. And there it is, right along with the B field. Okay? And so that's your growth of magnets. And so you can actually make something magnetic that way. In fact, you can actually take a material that was originally non-magnetic. You can apply an extremely strong external field to it while it is melted. And then you continue doing that, allow it to freeze or allow it to go back to a solid form, and you create yourself a permanent magnet. You can actually create a permanent magnet this way. So this is something that is done. So you want to create a magnet, sometimes you can take a material, we can create a magnet. Take a material, melt it, and then apply a strong magnetic field to it, allowing enough time for the material to magnetize, and then let the materials solidify again. So you will have created, and then you can pull the magnet away. So you can turn off the external magnetic field. So you can finally turn off the external magnetic field. And you will have created a permanent magnet. So in fact, you actually can use this very technology to make your own magnets, and you can make them as strong as you like. So this is something that has been done for many years, decades, in fact. We can create magnets. We can make them in this very manner. Now, you also have, so that's ferromagnets. You also, as we understand, people began to understand that there is a relationship between magnetism and electricity. So again, it was for many, many centuries, it was thought that electricity and magnetism were totally separate entities. But however, there's certain phenomena that happen that you have to try to explain. For instance, if you walk into a strong thunderstorm, carrying a magnetic compass. Again, we use compasses to as you know, to determine the direction of magnetic field. So you're carrying a magnetic compass in your hand. We'll say a compass. Compass means magnetism. You're carrying a compass. And the purpose of a compass is that its needle points in the direction of the magnetic field. So let's just say, for instance, we'll say you walk into a strong thunderstorm carrying a compass. Purpose of a compass is that its needle points in the direction of the magnetic field. You will find that a lightning bolt will cause the compass to spin around. It'll go haywire. Why does that happen? So we know electrical, we know lightning bolts are electrical, aren't they? Why would they spin around a compass? So a compass only reacts to a magnetic field. So is there a corresponding magnetic field with a lightning bolt? Well, we'll find out that there is. In fact, so the very first ever scientist to actually show through an empirical evidence that there is such a relationship between electricity and magnetism was a gentleman by the name of Hans Christian Ørsted. So Hans Christian Ørsted, so the Danish physicist, Hans Christian Ørsted, he lived from 1777 to 1851. He found that a compass was deflected by a current carrying wire. All right, so there is a relationship between what we thought was purely electrical and magnetism. We don't yet understand what that relationship is. However, it was interesting is that it was actually exploited quite a bit before we understood it. I mean, so it didn't stop. So not understanding the relationship between electricity and magnetism did not stop Samuel Morse from inventing the telegraph. So, I know today we can go to our cell phone and send a text message, or we have all this great technology, but, back in the 1700s, you literally had to go and write a letter and put it on the Pony Express. You had to go write a letter, and somebody had to deliver that letter via horse. To actually have wires go all the way across the country and eventually even to Europe and send an electrical signal across and have that electrical signal deflect a magnet to basically drop a hammer to either make a dash or a dot across the country, possibly across the ocean, Atlantic Ocean, and have that happen like around light speed was absolutely incredible. And so this was a relation between electricity and magnetism that was exploited. The fact that you can take a current and you can make a magnet cause a deflection of something that's like an ink blotter to either drop a dot or a dash, what we call Morse code, is an incredible development in history. And it wasn't understood why that worked. All right, and so we actually can create magnets through electrical currents. So electromagnetism, I use that word roughly, but electromagnetism is the use of electric current to make magnets. And again, we'll explain this more in detail as we go along. So it's the use of electric currents to make magnets. All right, that is the concept of what electromagnetism actually is. And so we create such magnets. So magnets created this way are called electromagnets. We have ferromagnets and electromagnets. These are non-permanent magnets. You have to have a current in order for you to have electromagnets. And so, electromagnets are employed. Probably the most famous one is, picking up junked cars. So electromagnets are employed in everything from lifting junked cars by a crane to controlling powerful extremely charged particles in an accelerator, particle accelerator. That also is it. 2, the magnets used in medical devices. All right, so we have magnets of 2 different kinds, you know, and again, they work really the same way. I mean, you know, when you study magnetism, you don't really care how your magnet was caused. You just care about, well, what's the behavior of the magnetic field. So you'll get the magnetic field one way or the other. We're just kind of showing you how you get magnetic fields. Some of them occur naturally. Some of them you get through by employing a current, usually in a loop. All right, so we have this concept of magnets. We understand a magnetic force. We understand that there's a magnetic force that attracts or repels. So of course, just like in you know, in the case of electricity, you know, we understood that you could charge objects, and there is a repulsive or attractive force between them. We characterize that force. We will characterize the force also between in magnetism. And what's very important in electricity is the concept of electric field. And again, electromagnetic theory is a field theory. So just like it's very, very important to understand electric field and electricity, we need to understand the magnetic field and magnetism. We have the combination. We have this concept of the magnetic field. All right, so let's go talk about that now. And we're going to see there's a lot of parallels between our study of magnetism and our study of electricity. All right, and so magnetic forces just like electric forces cause action at a distance. Okay, and so just like with electric forces, we can define a field. So just like I said, just like electric forces, we can define a field for magnetic forces. Which we call a magnetic field. And we usually denote it by the letter B. So, and it is a vector, so we sometimes refer to it as the B field. Whatever reason, the convention in physics is to denote the magnetic field by the letter B, capital B. All right, so we have a magnetic field. And you actually can understand the magnetic field by understanding magnetic field lines. Just like with electric field, we talk about magnetic field lines. So that's a very important way, because again, you can't really see an electric field or a magnetic field. All you can really do is map out the effect that they have in the case of electric field, we mapped out the effect it has on a positive test charge, a small test charge that's small enough not to affect the experiment. Well, for the magnetic field, we actually we'll map it out with what's a little compass. We use little compasses, small enough not to affect the experiment. So we're going to use the concept of magnetic field lines. So again, we'll get into that now. So with an electric field, we're able to map out the electric field lines by using a small positive test charge Q and noting the force, magnitude and direction, that it experiences at different locations in space. And note, we used a relatively small positive test charge. So we used a test charge of relatively small magnitude so as to minimize its effect on the experiment. Okay, so again, with electric fields, we can't see an electric field. We can only put a test charge in a whole bunch of locations and note what direction the test, what's the magnitude and the direction of the test charge. We can map out the electric field. We go around a positive point charge, so say a positive point charge capital Q. Everywhere we go, we can see that the closer, it's kind of like the experiment we did for electric fields. The closer that the test charge is to the point charge, the greater the magnitude, and the further it is, the smaller magnitude. And we also saw that the direction was always radial. And you saw this by doing what? You mapped out a little positive test charge, because you can't see the electric field. You can only see its effects. Well, you have to play the same game with the magnetic field. But in this case, you don't use a test charge, you use a test compass. All right, and so we utilize a small test compass at different locations with respect to a magnetized object in order to map out the magnetic field lines. I mean, you can't see the magnetic field, and so all you can do is see its effect on a bunch of little test compasses. So, for instance, let's look at a bar magnet. So we have a bar magnet. We know it's magnetized, but can we understand the magnetic field about the bar magnet? So we'll take, for instance, a bar magnet. Regular bar magnet like you have on your refrigerator. All right, common magnet, first magnet most people experience. And so what's a bar magnet look like? Well, again, it's just a bar, has a north pole and a south pole. And I'm going to go and start looking at little test compasses. And so I'll put a compass here, and I see that directions, let's say this direction. All right, and I put another compass out. Compass points this way. And I look around and I see the compass and I continue mapping in a very, meticulous way around the magnetic field. And I do this very, very meticulously. My drawing's not very good, but you'll notice that as I map around the field, my compass points in various directions. If I map this out by, instead of drawing now a corresponding line, a couple of lines, let me now draw out the field lines that I've now determined carefully via experiment. So I redraw my bar magnet best I can. Now I say, well, what exactly does this look like? Well, I have my north pole, my south pole again. The magnetic field lines will come out of the north pole and come back into the south pole. So they're coming out of the north pole and they come back into the south pole. And in fact, one of the things that I would notice that if I was actually able to look inside the magnet, if I can actually look inside, I would find out that there is no beginning and no end to these lines, that they actually form loops. But what I notice is that magnetic field lines I'm going to be very careful with my wording here. Magnetic field lines begin at a north pole and ends at a south pole. I am being very careful not to use the word terminate, because they really don't, because they actually form loops. So magnetic field lines, so electric field lines, we recall, begin on positive charges or on a positive charge and end on it and terminate on a negative charge. for comparison. We are not beginning or ending on charges in for a magnetic field because we don't have magnetic charge. Magnetic charge, there are no magnetic monopoles. There is no such thing as a magnetic charge. Magnetic field lines form loops. They form closed loops. With no beginning or end. I gotta be very careful with my verbiage because begin and end, you know, is very loose. And that's the beginning and the end that I can actually see from the bar of magnet. I can't actually look inside of it. But in reality, they actually form loops. They are continuous loops. All right, and so let me, without beginning. So this last statement says with no beginning or end. It's hard to see on the glare there. So again, magnetic field lines form closed loops with no beginning or end. That is the difference. All right, and so now, and again, in any kind of arrangement, you will form these. You actually will take a look and see what the magnetic fields do. I mean, how do they form? And so you find out that, for instance, let's say, for instance, I take a loop of wire, and I ask the question. Let's look at another example of what happens. What would I see around a loop of wire? Here's another example. Again, we're going to show you what you would see experimentally, then we'll give you the theory. So let's take a loop of wire. Let's kind of imagine if I draw a loop in the board here. A loop of wire with a current I. Another example. So I'm going to try to draw the loop as if it's plane to the board. And that's supposed to be a loop. It's kind of like, plane to the board. Okay, so again, we have a loop with a current going this way. We would actually find out that in any given part of this current, if I pick this part of the current, I would actually have a magnetic field going around looking like this, and it would have, look more symmetrical, of course, and it would literally be going in this particular orientation. That's your magnetic field if I took it at this particular part of the wire. If I went to another part of the wire, what would it look like? Let's kind of go over here, for instance. It will look like this. And they form loops about the wire. Now, again, we're going to show mathematically why this is. But I would anywhere I would pick about the wire, I'm going to see these loops. Again, I'm going to see these loops. So if you imagine a wire going this way, the magnetic field is going to be going circularly around the wire. So it's always going to be going circularly. Now, if I imagine a long straight wire of current I. Okay, this is experiments I'm doing. We'll say carrying current I. So now I'm going to imagine a long wire going like parallel to the whiteboard. Long, straight wire. Okay. And this wire is carrying a current I straight up. I will find out that the magnetic field is actually going in concentric circles about the wire. Concentric circles about the wire. All right, just like that. So I will find out the magnetic field will form a loop. about the wire. And it's me going like this, and I'll explain how I understand the direction of this current. So again, the magnetic field is going to be going like this. I'm going to explain what's called the right-hand rule in a moment. Well, remember our right-hand rule. We're going to be using that right-hand rule again. So again, if I have a long straight wire, I'll have the magnetic field will form concentric circles. So the magnetic field forms concentric circles. About a long straight wire. Again, we're just doing experiments. We haven't done any math yet. We haven't done any theory. I'm just taking out experiments. Well, let's try a long straight wire. Well, look at that. The magnetic field forms concentric circles along a long straight wire. And it goes this direction all the time. The current's going this way, the magnetic field is going to go this way. The current's going this way, the magnetic field is going to go the other way. How interesting. Or if I look at a wire loop, another important application. Again, the magnetic fields are always going to be going in circles around that loop. All right, so these are experiments that I'm doing, and I need to understand why all this is happening. And all I'm able to do is essentially take a little compasses out and map magnetic fields. That's all I'm doing. I'm mapping magnetic fields with little compasses. All right, so when you're looking at magnetic field lines, there are rules that you need to adhere to, just like you do with electric field lines. All right, so what are the rules for drawing magnetic field lines? We have 4 of them. So rules. Again, rules. Sort of spacers. I have 4 rules to write. So rules for drawing magnetic field lines. Just like electric field lines, we also have some rules in drawing magnetic field lines. All right, the rules. Number 1. The strength of, the direction of the magnetic field. Is tangent to the field line. At any point in space. A small compass will point in the direction of the field line. A small compass will point in the direction of the field line. All right, rule number 1. Number 2, the strength of the field. Is proportional to the closeness of the lines. It is exactly proportional to the number of lines per unit area. It is exactly proportional to the number of lines per unit area perpendicular to the lines. That's called the areal density. Okay, there you are. Number 3. I have enough space. Magnetic field lines can never cross. All right, so this is the first 3 out of 4 rules, and they're just like the electric rules, all right? The direction of the magnetic field is tangent to the field. The direction of the electric field is tangent to the electric field line, right? The magnetic field line shows you where the magnetic field is going, where it is heading, its direction. Just like the electric field line shows you the direction of the electric field. All right, so again, in the case of, you use a small compass now to point in the direction of the magnetic field line. So the direction of the magnetic field line is tangent to the field, means it's along the field. Or sorry, it's tangent to the electric, so the direction of the magnetic field is right along. Tangent to means basically in the same direction as the field at any point in space. A small compass will point in the direction of the field line. So again, as I showed you, you use little compasses to point where the field direction is going. Number 2, the strength of the field is proportional to the closeness of the lines. It's exactly proportional to the number of lines per unit area, called perpendicular to the lines. Again, that's exactly the same as electric field. The number of electric field lines that cross a perpendicular area is proportional to the strength of the electric field. The number of magnetic field lines that cross a perpendicular area is exactly proportional to the strength of the magnetic field. So far, these are the exact same rules. Magnetic field lines can never cross. Electric field lines can never cross. Again, exact same rules. If the magnetic field lines crossed, there'd be an ambiguity. I mean, if you have crossing magnetic field lines, just so electric field lines, they're supposed to be unique. If I don't know which direction, I mean, I have an ambiguity. Is it this way or this way? Because the direction of the magnetic field is always, and there's only one direction it can be at any given point in space. You can't have 2 different directions. So the magnetic fields actually crossed in space, there would be confusion. You wouldn't know which direction the magnetic field was. So again, these are all the same rules that apply to electric fields. Now, rule number 4 is going to be what's unique to magnetic fields. So again, these are the first 4 rules. I usually like to write all 4 of them in the same location, but real estate. So let's look at number 4 now. So rule number 4. So rule number 3, we're all familiar with these rules for electricity. These are the same rules that you'd write down for electric field lines. Nothing new. That is how magnetic field lines, electric field lines behave that are in a similar way. And number 4 is going to be unique to magnetic field lines. Rule number 4 says magnetic field lines are continuous. Forming closed loops without beginning or end. Without beginning or end. So again, that's what's different. And I showed you that in a picture I wrote earlier. They go from the North Pole to the South Pole. Okay, so that's what's different, because electric field lines did what? They started on a positive charge and terminated on a negative charge. Magnetic field lines do not start or end, they only form closed loops. Okay, and they'll start from, from where you look at it in a magnet, they will come out of a North Pole and they'll go into the South Pole. So they leave a North Pole, they emanate from the magnet at the North Pole, and they come back around at the South Pole. Okay, and so now if magnetic monopoles existed, they would actually come off magnetic charge and go to a magnetic charge. So again, the magnetic field lines always leave a North Pole and go to a South Pole. So I'll write that down. So magnetic field lines always emanate from a North Pole. And re-enter at the South Pole. So a compass needle points along the direction of the magnetic field at a location in space. So something interesting here. What if we're talking about the Earth's magnetic field? So you're saying that the magnetic field, the compass needle points in the direction of magnetic field. Well, so here's what's interesting. If I were to go in and do what? I would go and use a compass. What would it do? I would be pointing and it would show me what? The direction of the North Pole, right? So if we're saying that the compass points in the direction of the North Pole, it would point in the direction of where the magnetic field lines are going, which will be to what we call the North Pole. So what's funny is, if you look at the Earth, for instance, so on the Earth, say I'm sitting here in Texas, and I say, okay, yeah, I'm over here, and I have this my little compass is sitting right there, and it's pointing, what I call north, and we will refer to this as the North Pole and the South Pole, right? Well, let's think about it. If the field lines are heading this way, that means that the field lines are really emanating from the south and heading to the north. Right? So that really means that what we call the North Pole is really a South Pole. Why? Because the magnetic field lines are actually coming out of what we call the South Pole. And they have to be. Why? Because I'm here in Texas and I'm getting out my compass and it's pointing what? It's pointing along a magnetic field line, isn't it? And I always say, oh, the magnetic field line points to what we call North Pole. What we call the North Pole, what we call north, right? Well, we may call this direction north, but if you look at the Earth as a big bar magnet, the North Pole is really the South Pole of its magnet. So the North Pole, the Earth's North Pole, as we say, where the polar bears live, is really its magnetic South Pole. And the Earth's South Pole, where the penguins live, is really its magnetic North Pole by our definition of magnetism. Right? So again, you know, the magnetic field has to emanate, it's going toward what we call the North Pole, but it really should be going to a South Pole of a magnet. All right, so that's kind of a little interesting piece of information. We kind of got it messed up. All right, so let's now go to the mathematics of the theory. Okay, so before we do that, let's remind ourselves about vector multiplication one more time. All right, so let's remind ourselves that, talk about vector multiplication. So remember, vectors multiply two different ways, right? We have what's called the scalar product. All right, that means that's vector times vector yields a scalar. Again, this should be pretty familiar with us now. So if I take two vectors in space, A and B, and they have an angle theta between them, the scalar product, we also call it, the vector product, we also call it the dot product, because we use the dot symbol of multiplication. We would say literally, again, A dot B, you would literally write this as A dot B. That's how you would say it. A dot B, remember, is the magnitude, and take the hat off, the magnitude of A, the length of A, its magnitude, times the magnitude of B, just a regular product, times the cosine of the angle between them. A is a scalar, B is a scalar, cosine is a scalar. I get a scalar out of it, right? Examples of this, again, work is one. We know that work is the dot product of the force and the displacement. Another example is Gauss's law. Remember Gauss's law? We would divide up a electric charged object into little tiny areas. We have a charged object. We divide it up to little tiny areas all over the place. Each of these areas has an area normal. We'll say this is A sub I. You know, again, I as a counting number, 1, 2, 3, 4, whatever. This is the ith counting number. And there is an electric field, E sub I. And they're hypothetically at an angle theta. So we'll call it maybe theta sub I, whatever you want to call it. And I would literally say that the summation, again, this is going about a Gaussian surface. Again, it's the little thin skin that I draw all around my charged object. Again, this is the Gaussian surface. What did I say? Well, Gauss's law is what? It's the sum of all of these E sub i's, electric field going through. Each of these areas is so small, we can imagine it just having one electric field vector. Dot product with its corresponding area normal. All right, and we know that's equal to the charge enclosed in the Gaussian surface divided by the permittivity of free space epsilon naught. Again, what are these? These are nothing but a bunch of dot products. And so we see that dot products are indeed useful in electromagnetic theory. We've seen that many times. Now, we also know about the other form of multiplication. We haven't talked about that yet. We're about to. And that's called the vector product or the cross product. And so we did talk about the cross product in back in physics 1, because we did talk about torque, and we also talked about angular momentum. So we have another form of multiplication, and it is called the vector product, otherwise known as the cross product, because we use the crossbow or the crossbuck form of the multiplication symbol. So cross product, vector product, also known as a cross product. Kind of reminder of what we did, and we have talked about this before in physics 1. We haven't really talked about it much in physics 2. That is literally a vector times a vector gives you a vector. Now that might be what you normally would think. Usually you say, oh, integer times integer gives me integer. Real number times real number gives a real number. Fraction times fraction probably gives me a fraction. Again, the two things that go in, usually the product is the same kind of form, right? Well, it's kind of weird how you'd have a vector times a vector giving you a scalar. In this case, you have vector times a vector giving you a vector, which you might expect. But the problem is, this is a vector that you might is different than the vector that you might expect. So again, if we go back to an example of two vectors, let's say A and B. So I have two vectors again, vector A and vector B. Same as the example before, and I have an angle theta between them. Cross product literally says, I would literally say A cross B. And I would literally state it. So I have A cross B. And I would literally say A cross B. I literally would say it just like that, because I'm using the cross product. A cross B, again, is the magnitude of A times the magnitude of B times the sine of the angle between A and B, which is theta, in a direction. Perpendicular to the plane formed by A and B in accordance with the right-hand rule. All right, so we may have ignored this before, but no longer. Right-hand rule and the cross products are going to be very, very important from here on out. So what does this mean? Well, the way I have this drawn, I have A and B drawn in my whiteboard. I have to use my right hand. And what do I do? Well, I say, well, A and B is, the magnitude is this, that's pretty simple. A times B, magnitude A times A, magnitude B times the sine of the angle between them. But then the direction, well, first of all, the direction is perpendicular to the plane. Well, if A and B are in the whiteboard is my plane. Okay? So perpendicular to the plane means what? It means either straight out of the whiteboard or straight into the whiteboard. Which is it? Well, the which is it is answered by the right-hand rule. So I literally will use my right hand. I cannot use my left hand, my right hand, and I will go from left to right. I put my fingers along the first vector. Reading from left to right. My first vector, oh, it's A. Good. I put my fingers along A. And I cross them. I curl them toward the second vector, which is B. And the direction of my thumb is the direction in which the vector points. So again, I'm going to try to draw this here, line up with my drawing here. So here's A. I line my fingers up along A. I curl my fingers from my right hand along B. And the direction of my thumb is into the whiteboard. It is perpendicular. Is it, you know, again, there's an ambiguity. It's either out of the whiteboard or into the whiteboard. My thumb is into the whiteboard in accordance to the right-hand rule. That's the direction in which A cross B points. It is mutually perpendicular to A and B, and it's in the direction in accordance with the right-hand rule. Now, again, in algebra, you know, you study algebra as you know, you're younger, back in middle school and high school. You know, you realize that, you know, you could say A times B equals B times A, no problem. Commutativity is perfectly okay. Well, in higher mathematics, commutativity of multiplication almost always generally fails. All right. And so if you look at A cross B, you say, okay, I have a vector that's pointing into the board. But in general, for more advanced mathematics, for more advanced mathematical objects, commutativity of multiplication generally fails. In general, A times B is not equal to B times A. It's almost never true for matrices. And it's generally not true for vectors, particularly cross products. In fact, for cross products, we actually say it's anti-commutative. Let me keep my same picture up. Let me kind of reverse things and say, hey, I don't want A cross B now. Now I want B cross A. I want to calculate B cross A. Well, what do I do now? Well, again, it's the magnitude of B. Take the hat off. Times the magnitude of A times the sine of the angle between A and B in, you know, in the direction or perpendicular to the plane formed by A and B, or I should say B and A, according to the right-hand rule. Just like I said before. All right, well, how do I do this now? Well, I will line my fingers up. I'm going to read left to right. I line my fingers up with the first vector B. I curl them into the direction of A. And my thumb points out of the board. My thumb points out of the board. So basically, I start with vector B. I curl toward vector A. My thumb points out of the board. So in fact, before my thumb pointed into the board, so in fact, because of this, we actually say that A cross B and B cross A are cross products are anti-commutative. Anyway, they're anti-commutative, so cross products are anti-commutative. Which means that A cross B is equal to negative B cross A. Okay, so A cross B is negative B cross A. They're anti-commutative. Give me a moment here. All right. So how does this have? What does this have to do with electromagnetic theory? Well, electromagnetic theory, we find out that the actual magnetic force is based upon a cross product. So essentially, the magnetic force, again, this is all determined through experiment, but the magnetic force is F sub B. Again, I put a little b for magnetism. That's equal to Q B cross B. Okay, so if a charge Q moves in a magnetic field of strength B, or we'll say a magnetic field B, it experiences a force, a magnetic force given by F sub B equals QB cross B. Okay, so that is, so essentially, in order to play in electromagnetic theory, you have to have a charge. You have to have a charge Q. Now, if the charge Q, if you have a charge in a magnetic field, the charge Q isn't moving, it doesn't experience a force. That charge has to be moving at a velocity V. There has to be a magnetic field B for there to be a magnetic force. So you have to have a moving charge, and it's given by whatever the vector, the velocity vector is, cross product with the magnetic field in that region. And you multiply that by the charge of the charge of the object that's moving, and that is the magnetic force that it'll experience. All right, and so again, the angle theta, so this will be given by, it's to be mapped out as, F sub B. If you look at the magnitude of F sub B, it would be Q B B sine of theta, where theta is the angle between V and B. So again, theta is angle between V and B. All right. So again, you know, if you had any doubt of the importance of the cross product, you see that one of the fundamental forces of the universe invokes a cross product. This actual force law is named the Lorentz force law. There is a brilliant physicist, Dutch physicist by the name of Henri Antoine Lorentz. He was a contemporary of Albert Einstein. He was much older than Albert Einstein. I think he got the 1902 Nobel Prize in Physics, but he is big on relativity and quantum mechanics. Well, actually, he has his name on a lot of things, actually. Electricity or electromagnetic theory, relativity, and quantum mechanics. So Lorentz was an extremely important figure in physics. So Henri Antoine Lorentz, you know, he was somebody who was a big supporter of Albert Einstein too. All right, so Albert Einstein, when he came up with theory of relativity, which we'll talk about when we get to chapter 28, a lot of people were like, "Oh, what is this about?" You know, it was a redefinition of a worldview. And a lot of times, you know, anytime you redefine a worldview or try to in a very, you know, dramatic way, there's always rejection of it, right? And so Einstein received a lot of rejection. Now, if you want to figure out, we are now in a position to figure out what are the units of a magnetic field. So if I go back and I say, well, let's look at the magnitude now. So I have the Lorentz force law. The magnetic field is Q B B sine theta. Okay, so again, we're not going to worry so much about sine of theta. You know, that doesn't have a unit. So let's try to get the units of the B field. So B, simply solving for it, S of B over QV sine theta. All right. So let's take a look at this here. So what are the units? So I have the units of the magnetic field. Let's work this out. I have newtons, clearly, for the force. I have coulombs for the charge. I have meters per second for the velocity. All right. And so let's see, coulombs per second is what? That's an ampere. So I can actually write this as a Newton per ampere meter. All right. Now, when you see a combination of those units, and as it regards to magnetism, we honor the great Nikola Tesla. So when we take this together, we refer to this as 1 Tesla. And we use a capital T. All right, so 1 Tesla is 1 Newton per ampere meter. It is the base unit of the magnetic field. It is the official SI unit for magnetism, for the magnetic field. So again, the official SI unit, now Tesla is a very large magnetic field strength. But again, the base unit of magnetic field is the Tesla. All right, so the base unit of the magnetic field is the Tesla. Named after Nikola Tesla. And I talked about him, the great Nikola Tesla. Pioneer in electricity and magnetism. So again, 1 Tesla is 1 Newton per ampere meter. All right, a Tesla is a large magnetic field. We often use another magnetic field called the Gauss. One Gauss, named after Carl Friedrich Gauss, one Gauss is equal to 10 to the negative 4 Tesla. All right. And in fact, oftentimes devices used to measure magnetic field are called Gauss meters. So we call devices used to measure magnetic field. Magnetic fields are Gauss meters. All right, so use a Gauss meter. We oftentimes see that in computer science. You might say you'll de-Gauss something. Again, it's dealing with magnetic fields. So a Gauss meter reads a magnetic field. So you'll look around and you figure out what the magnetic field is. Like let's say some location on the Earth. So again, one Gauss is 10 to the negative 4 Tesla. That Tesla is the unit of magnetic field. So you have units of B, you have the Tesla. All right, I'm going to work out a few problems now from OpenStax. It's time to work out some problems. So I'm going to look at OpenStax 22.1. Let's start from the beginning, most basics. Let's get kind of our fingers wrapped around the concept of these of this cross products. All right, so OpenStax 22.1. That says, what is the direction of the magnetic force? On a positive charge, that moves as shown in each of the 6 cases. That moves as shown in each of the 6 cases shown in figure 22.50. So again, if we were doing OpenStax, we would be in chapter 22 already. Here in our book, we're in chapter 21 still. Okay, so again, I'm going to draw you 6 pictures. Normally, this is a good class exercise. Usually if I'm meeting face to face, I have the class help me figure this out, right? It's a nice class exercise. So what is the direction of the magnetic force on a positive charge? Again, emphasis on positive. That moves as shown in each of the 6 cases shown in figure 22.50. So let me draw these cases out one at a time. All right, so first case that we will show is going to be the B field. So the B field is going to be given by these little dots. And I'll explain this in a moment. So again, this is a demonstration of the B field in this region. Draw a few more. And that's my B field. And my velocity is going straight down. All right. Now let's let's look at the nomenclature here of what this means. All right. So imagine for a moment an arrow. Okay. So I have an arrow, and we kind of look at an arrow like a little arrow that in archery, for instance. You have an arrow, and the arrow has a head to it, and it has tail feathers. Right. So imagine there's an arrow like an archery. All right. if the head of the arrow is coming at you, what would you see? You'd see a dot coming at you, right? Head of the arrow is coming at you, you'd see a dot. If the arrow is heading away from you, you see the tail feathers, right? So arrow coming toward you, you see a dot. The arrow coming away from you, you see the tail feathers. So what this means is that, you know, we're looking at the whiteboard. Out of the plane of the whiteboard, the magnetic field is coming out perpendicularly. These dots basically mean that the magnetic field lines are coming at you like archery arrows. All right, they are coming out perpendicularly. So again, when you're talking about, because this is such a vector nature theory, what you want to do is you want to establish what is your orientation, number one. All right, so I'm going to kind of establish an orientation here throughout all of these 6 cases. I'm going to say that positive x hat is to the right, negative x hat is to the left, positive y hat is up. Again, I'm in the whiteboard now. I'm still in the plane of the whiteboard. Negative y hat is straight down. And then positive z hat is out of board. Negative z hat is into board. Board being in the whiteboard. So let's look at this for a moment. Well, I would explain that B in this picture is in positive z hat direction. And I would say that the velocity is in negative y hat direction. Again, the velocity is in the plane of the board going down, negative y hat. The magnetic field lines are all coming out of the board. Now, what is my formula again for force? I want to find the force. So the magnetic force is Q B cross B, and Q is positive. Very important. Well, let's see here. I take my right hand and I follow it along as I would. I would say, okay, and this is going to be kind of hard to demonstrate. So Q cross B. So I take my right hand and I point straight down for Q. For V. B is down. B comes first. B cross B. QB cross B. B comes first. So my right hand has to go straight down. Now, it's got to curl inward, or I'm sorry, outward for B. My thumb is going to point to the left. So if you look at this again, my hand is straight down. Okay? And my hand is straight down. That's going to be QV. Cross where? Fingers cross out. My thumb points to the left. All right? So again, QV. V, straight down. QV, left to right. Cross, well, my hand is going to go such that my hand is going to, so I have to cross outward. Because why? Because B is straight out. And then my thumb points to the left. So the force, the magnetic force, is in negative x hat direction. We'll try to stand up and do this. It's better. All right, and so again, I have to do it in order here. So imagine QB, straight down. B, cross B. B is going where? It's going out of the whiteboard. Curl my fingers out. My thumb, because of the anatomy of my right hand, my thumb is now going to point to the left. Negative x hat direction. Okay? And so again, that is where the force is going to go. The magnetic force is going to go in a negative x hat direction in accordance with the right hand rule. All right? That's the first problem. Again, QB cross B, cross product. Let's look at B. So B, I'm going to keep my orientation. Oops, I just erased my Z's. Restate that. So again, positive Z hat is out of board. negative Z hat is into board. All right, that's my orientation. Now, that was A. Here's B. Part B says I have magnetic field that's going to be going in the X hat direction. So here's my magnetic field lines. And my velocity is straight up. So again, the B is in X hat direction, positive X hat. Velocity is in Y hat direction. Again, so I'm going to be careful here. This is positive X hat. Velocity is positive Y hat. All right. What is my formula again? Force, magnetic force is QV cross B. Again, the charge is positive in this case. All right, well, let's see here. I line my fingers up with the first vector, V. What's that going to be? It's going to be straight up. There's V, straight up. And I curl them in the direction of B. So V is straight up. And I curl in the direction of B. V cross B. B. Again, B is straight up. Where's my thumb going? My thumb is going into the board. So F, the force is in the negative Z hat. Again, I have to read the right-hand rule left to right. So again, V, QV, again, I'm not going to worry about Q because Q is positive. V, line my fingers up with V, right hand. I cross them toward the second vector. In this case, B is to the right. So V, cross B. Where's my thumb pointing? Of course, my anatomy of my right hand is pointing into the whiteboard. Into the whiteboard means negative Z hat. Okay, let's look at the third example, part C. Part C says, what I have now is I have a magnetic field going into the board. I see tail feathers. Okay, into the board for the magnetic field, and the velocity is heading to the right. All right, and this is the magnetic field. The tail feathers say that when you're looking at tail feathers, you're seeing the arrows going away from you. So the tail feathers means into the board. So B is in the negative Z hat direction. V, the velocity, is in the positive Z hat direction. I'm sorry, positive X hat. So again, the magnetic field is in the negative Z hat directions, into the board. That's what the tail feathers mean. And the velocity is to the right, that is positive X hat. Again, I have to take the cross product in order. So again, what do we have? Lorentz force law says the magnetic force is Q, V, cross B. Okay, so again, I gotta go in order. So the velocity, I start off by lining my fingers up along the first vector, left to right, that's V. And I cross it in the direction of magnetic field. So here's B, cross, so V, QV, cross B. My thumb points up. Again, QV, cross B, going into the board, QB's to the right, cross the second vectors into the board, that's B. And where does my thumb point? Because I'm not having my hand, the thumb points up. That means that my magnetic force is straight up. What's that? Positive y hat. All right, so again, I have to use the right-hand rule to do this. All right, letter D is a little bit different. And so let me get this out here. So let's draw the next one. Letter D. Letter D is saying that I have magnetic field to the right. That's my magnetic field. And it turns out that my velocity of my particle is going straight to the left. Now, looking at this, I have force is QV cross B. Again, as always. Well, what do we know? Well, we know that the magnetic field is in positive x hat direction. The velocity is in negative x hat direction. These are anti-aligned. So when I go to any other thing I've been doing here, they're at right angles. These are anti-aligned, and that the angle theta between V and B is 180 degrees. Well, if I look at this, I say, well, okay, force is QVB. If I say, well, force, this is look at the magnitude, that's QVB sine of 180 degrees. Well, if you plug in your calculator, the sine of 180 degrees, you get 0. That means the magnetic force is 0. You cannot take a cross product of a unit vector with itself. If it's aligned or anti-aligned, unlike with dot products, if they're aligned, you have the maximum dot product. That's right, because the cosine is 0 or cosine 180 is 1 or negative 1, right? However, for sine functions, the sine of 0 or the sine of 180 is 0. So if you have a situation where you have something like x hat cross product with, let's say, negative x hat, that's 0. Or if I have x hat cross with x hat, that's 0. Or if I have y hat cross with y hat, it'd be 0. I mean, again, if I do a cross product between two vectors that are either aligned or anti-aligned, I get 0 as my answer. Because they are at 180 degrees, or if they're aligned, they're at 0 degrees angle, and if they're anti-aligned, like in this case, they are at 180 degree angle. The sine of 0 is 0. The sine of 180 degrees is 0. So if you have a velocity and a magnetic field that are aligned or anti-aligned, the magnetic force is 0. There's no right-hand rule to even be worried about. So in this case, the answer is simply F sub B equals 0. There is no magnetic force in the situation. All right, let's look at E, part E. Oh, that was part D, I'm sorry. The last one was part D. Here's part E. Part E has the magnetic field going straight up. That's your magnetic field. And your velocity is going to be going into the board. That's your velocity of your particle. All right, so what do we know? We know the magnetic field, according to my orientation, magnetic field is in positive y hat direction. The velocity, I'm seeing tail feathers. So the velocity is in negative z hat direction. What about my force? Again, what do we know? It's the force, the Lorentz force law is QV cross B. All right, so I have to do it in order. So now I line my fingers up in the direction of the whiteboard. So right now, that's V. I have to do V first because it's in order, left to right. So B cross what? Well, B is going to go up. So I go QV cross B, which is going up, and my thumb points to the right. Again, QV cross B. I cross it in the direction of the second vector. My thumb, by anatomy in my right hand, again, I have to use my right hand, not my left hand, my right hand. The anatomy of my right hand says that my thumb points to the right, which is positive x hat. So my force is in positive x hat direction. All right. And finally, I have letter F. Let me draw that. So for letter F, we have the magnetic field heading to the left, or negative x hat. My magnetic field. And my velocity is straight out. And the head of the arrow, the tip of the arrow is coming at you now. And again, what am I looking at again? The Lorentz force law says the magnetic force. Okay, let me write this down. So the magnetic field is in negative x hat direction. The velocity is in positive z hat direction. Now, as a general rule, you know, if you're talking about magnetic fields, x, y, and z always have to be represented, right? And so if you see x and z already represented, your answer is going to have to be something in the y. I mean, the magnetic field, the velocity, and the force are all going to have to be in their own coordinates. So the magnetic field takes up the x hat. The velocity takes up something in the z hat. So you know your answer is going to have to be something in the y hat. That's one thing. You know, there's a check. Yeah. The axis that has yet to be used here is y. So your answer is going to have to be something y. The question is what? All right. Well, again, I use the right-hand rule to determine that. I remind myself again what the Lorentz force law looks like. F sub B is QV cross B. And I say, okay, QV cross B. Well, let's see. V is going out of the board. So out of the board, and my magnetic field is going to have to point to the left. So V is going out of the board. The magnetic field does what? So V coming to you, cross B to the left, straight down. That is where the magnetic force goes. Again, QV, cross B, straight down. Again, you cross with the second vector. So we have the F is going to be the negative y hat direction. All right, and those are your answers. Now, we look at OpenStax 22.2 now, and it says repeat the same exercise you did in 22.1, but now for a negative charge. I'm going to go through the first one for you, and then we'll show a generalization. All right, so now we're going to let the charge be negative. So let me go and put up letter A again. All right, so now we're considering, so we're going to do 22.2. But now we're going to consider a negative charge Q. Remember the 22.1, the Q was a positive charge. All right, so part A, remind ourselves what part A looked like again. Part A was, let's see, we had magnetic field coming out of the board. That's your magnetic field. And the velocity was straight down. All right, now we go back to, let's kind of rewrite again. So out of the board means, again, magnetic field is in the positive z hat direction, straight out. Those are the head of the arrow. The velocity is in negative y hat direction, again, straight down in the whiteboard. Now, if we go back to our 22.1, we would say, okay, well, let's see, let's remind ourselves what we said in 22.1. We have force to B is Q, V, cross B. Now, if I look at the V cross B, again, what do I say? Again, I align my hands, my fingers straight down with, velocity, and I curl them in the direction of the magnetic field. So again, in this case, my magnetic field is out, so my velocity, I take my hand straight down, my velocity, that's velocity, V, and then cross B is going to be out, and I said that my thumb pointed to the left, right? Well, I do that exact same thing with the right-hand rule, but if the charge is negative, I take that answer and I flip it. So if I say QV cross B coming at you gives me, where's my thumb going? The anatomy of my hand, QV, V. So V cross B. So again, V is the first vector, cross going out. The anatomy of my hand says I point to the left. If it's a negative charge, flip it. I point to the right. So whatever my answer is, if the charge is negative, I flip it at the very end. All right, and so the answer would then be that V cross B gives negative X hat. Okay, it's going to give me negative X hat. I mean, just doing the cross product. So again, B, where's the vector going? Cross B, going out. My thumb is pointing negative. But then the negative, if it's a positive charge, I'm done. The positive charge means that the answer is to the left. But if the charge is negative, I flip it to the right. So the negative charge flips the answer. So F sub B is in the positive X hat direction. Okay, it is not negative anymore. I have to flip the answer to positive X hat. So the answer to part A in OpenStax 22.1 for the positive charge was negative X hat. The answer to 22.A for the negative charge, I'm sorry, back up. The answer to 22.1 for part A for the positive charge is the negative X hat direction. The answer to 22.1 for the negative charge is flipped to the positive X hat direction. The negative charge flips the answer that you get from the right-hand rule. Let's do, I'll do one more, and then I think the rest of them you can understand. So let me look at part B again, and then we'll find out what our answer is. So again, part B for the negative charge. To remind ourselves again, remember part B was the magnetic field all going to the right. and the velocity going straight up. Now, again, the magnetic field is in positive x hat direction. The velocity is in positive y hat direction. All right, so the answer's got to be something z hat, right? Now, in 22.1, we know, again, the Lorentz force law. We always go to that. QB cross B. Now, let's just focus on V cross B. V cross B, okay, so again, you know, going back to the right-hand rule, I put my fingers in the direction of the first vector, B, and I cross it into the second vector, B. B, cross B, would be negative z hat. So V cross B is going to be in a negative z hat direction. Okay, that would be my answer in part A. If I had in part B for problem 22.1, if I have a positive charge, but I have a negative charge. Since charge is negative, F sub B is in positive z hat axis. I flip the sign. If the charge is negative, I take my answer from the cross product and I flip the sign. So essentially, all of your answers, and at least parts all of your parts except D, part D, of course, are going to be the opposite. Part D was 0, and it's still going to be 0, right? Irrespective of whether the charge is positive or negative. Part D was the anti-aligned velocity and magnetic field. So all of your answers for parts A, B, C, E, and F are going to be the opposite of what they were in part A. So in part A, in 22.1, my answers were the following, with the exception of the again, I would definitely suggest going through this yourself, but if you look at your answers in 22.1, A, B, C, D, E, F, so 22 point, again, open stacks, 22.1, I look at A, B, C, D, E, and F. All right. And well, and I look at open stacks 22.2. And again, I look at A, B, C, D, E, and F. Well, what did I get for 22.1? I said the answer, again, this is all the directions of the magnetic force. Negative x hat, negative z hat, positive z hat, or straight up. For part B, part C was negative y hat. Part D was 0. Positive y hat. Negative x hat, negative z hat, positive y hat, 0, positive x hat, and negative y hat. Those are my answers for 22.1. Again, negative x hat, negative z hat, positive y hat, 0, positive x hat, negative y hat. My answers for 22.2, as you can imagine, are exactly the opposite. So this answer would be positive x hat, because it was negative x hat before. I had to flip it. Positive z hat. My C would be negative y hat. My D would still be 0, doesn't matter. My E would be negative x hat. My F would be positive y hat. I just take my answer for the positive charge. For the negative charge, I just flip it. All right, so that's all that's to that. So So a negative charge, you flip the answer at the very end. Okay, let's look at OpenStax 22.5. So we're gonna now be told what the velocity and the force is. Then we have to go figure out where the magnetic field is. All right, and so now it's OpenStax 22.5 says, and more right-hand rule, what is the direction of the magnetic field that produces the magnetic force on a positive charge as shown in each of the three cases? On the positive charge, as shown in each of the three cases in the figure below. Yeah, I'll draw you the figures. Assuming B is perpendicular to B. B is perpendicular to B. Alrighty, so here we go. What is the direction of the magnetic field that produces the magnetic force on a positive test charge, or positive charge as shown in each of the three cases in the figures below, assuming that B is perpendicular to V? All right, so we're going to assume that B is perpendicular to V. So again, we're looking at a positive charge. All right, and so let's look at the pictures. Look at A first. So A looks like the following. A, I have a, again, here's my orientation. Establish that real quick. Don't just start telling me about X hat, Y hat, Z hat without showing me what that actually is. Again, positive Z hat is out of board. Negative Z hat is into board, just like last time. All right. Now I have the velocity in the up and force to the left. Here's my magnetic force. I'll put it F. And here's my velocity. And the question is, what's B? I mean, I'm really looking at what? I mean, I have the force is Q V cross B. So what I don't know is B. I don't know what B is. I got to figure that out. You know, before I was trying to get F. Now I have the answer. I'm trying to figure out what magnetic field makes that answer. All right. So looking at this, I know that again, B is in positive Y hat, and F is in negative X hat. F's my answer. So again, F is where my thumb goes, right? When I'm doing all this right-hand rule stuff, F is the answer that I seek. So F, I should already be pointing my thumb and what am I saying? QV cross B, or V cross B. Again, Q is positive. So again, we assume, again, that Q is positive. All right, and so, well, my F is the answer. And again, it's going to be V cross B, wherever B happens to be, this is going to give me F. So I know that F's my answer, so I might as well put my thumb out there now in the negative X hat, and V is where I start. So V, now if F is my answer, really the anatomy of my hand determines where B is. I mean, if F is the answer, where my thumb is already pointing in the negative X hat direction, and the velocity is in the Y hat direction, then by the anatomy of my hand can only point inward. That means the magnetic field has got to be in a negative Z hat direction. By the anatomy of my hand has to, my hand points inward. So B, my answer here, is in negative Z hat, into the board. And that's how my hand bends. Again, my answer is where my thumb points. Negative X hat, as given. My beginning is where my fingers initially align, V. Now they're either going to cross one way or the other. Well, by the anatomy of my hand can only fold forward, which means that B's got to be in the negative Z hat direction. Okay, that's why you use the right hand rule, because your hand doesn't bend the other way. All right, so your hand, the anatomy of your hand forces it to bend forward. What about, okay, here's the next question, part B. That was part A, here's part B. B shows you a force that's into the board, see the tail feathers, and the velocity is straight down. And the question is, where is B? So again, I say to myself, well, what's the answer? Well, the answer is that my thumb's, how my hand is oriented, my thumb has got to point into the board. Now the question is, well, where's B? Well, B is initial orientation of my velocity. Remember, my answer is where my thumb goes. So my thumb is going into the board, and where's my initial velocity? Well, my velocity has got to be where my fingers start before they curl. So my answer is into the board. My initial velocity is straight down. Well, by the anatomy of my right hand can only curl to the left, right? And so by that means is that, okay, well, that means that so again, B is in negative Y hat direction. F is my answer. That is in, oh, I'm sorry, yes, that is in the negative Z hat direction. All right, so again, V is already in negative Y hat, F is in a negative Z hat. I use my right hand. Okay, my thumb is the answer. My thumb is, I already know the answer's got to be, it's got to be in the negative Z hat direction. So my thumb's got to point, I have to orient my hand. So let's see, my V is my first vector, that's going to go straight down. And my thumb is pointing into the board. Well, V is straight down, that's the beginning of the problem. My answer is into the board. So by the anatomy of my right hand, how do my fingers bend? They bend to the left. That means that the magnetic field has got to be to the left, or negative X hat. So the magnetic field is in negative X hat direction, again, by the right hand rule. Again, a lot of times people look at physics kind of funny when they're doing magnetism because they're always doing stuff with their right hand, right? All right, I have part C. What's part C look like? Well, my setup here is I have the force vector straight up, and my velocity vector is to the left. So I have a velocity vector to the left, the force vector straight up. All right, so I set this up, and again, I know that QB cross B, I'm looking for B. All right, and so I'm looking for B. So again, I know the answer. The answer is where my thumb points. So my thumb's got to point up. And then the whole problem, again, I got to use my right hand. The problem starts, again, I'm trying to orient this. My thumb, I already know the answer. My thumb points up, and the start of the problem has got to be to the left. All right, so my thumb points up. That's my answer. The start of my problem, V, the first vector, is to the left. By the anatomy of my right hand can only bend outward. So that means that, so again, my force vector is positive y hat. My velocity vector is negative x hat. So again, I use my right hand. I point my thumb at the answer. The answer is the force. Thumb is going to go up. Now I have to figure out, well, okay, my thumb's up. How do I orient the velocity? The velocity is where I initially lay my fingers. My fingers have got to go. So my thumb, my answer is straight up. My fingers have got to go to the left. So I have to bend toward the magnetic field. That means I bend outward. So outward means positive z hat. So by the right hand rule, again, straight up, my velocity is to the left, I bend outward. That's where my right hand, that's by the right hand rule, that determines that the magnetic field is in positive z hat direction. So again, I would practice a lot of these to get the feel of it, because using the right hand rule for the first time is a little strange. But again, that's how we do magnetism. All right, let me look at OpenStax 22.7. .7 says, what is the maximum force? On an aluminum rod, with 0.100 microcoulomb charge, that you pass between the poles of a 1.50 Tesla permanent magnet. At the speed of 5.00 meters per second. In what direction is the force? All right. Now we're actually going to calculate using the Lorentz force law. So again, what is the maximum force on an aluminum rod? So you have an aluminum rod with a 0.100 microcoulomb charge. You have a charged object, basically, that essentially flies through. So you pass between the poles of a 1.50 Tesla permanent magnet at the speed of 5.00 meters per second. In what direction is the force? So again, I always encourage students to do this. So draw yourself a picture. So a lot of stuff going on here. Draw a picture to figure out what in the world are we talking about. All right. So again, I'm going to erase this for real estate purposes. Let's draw a little picture. So effectively, I have poles of a magnet. Maybe it's a horseshoe magnet. So I got a north pole here and a south pole down here. And of course, how the magnetic fields are going to go, they're going to go basically out north into south. They leave north, they go into south, as all magnetic fields do. and I'm passing some some charged object through here, and it's going straight across at a speed v. Okay, that's what I know. I know that the charge on this object is 0.100 times 10 to the negative 6 coulombs. I know the magnetic field is constant. Magnetic field. We'll actually, just like I showed you how to make a uniform electric field, I'll also show you how to make a uniform magnetic field. We'll see that by the end of the lecture. So again, the magnetic field is at a constant 1.50 Tesla. And I know the velocity. The velocity, the magnitude of the velocity is 5.00 meters per second. All right, so again, this is a direct usage of the Lorentz force law. So Lorentz force law says that the magnetic force, F sub B, is QV cross V. All right, or basically it's Q, the magnetic force, F sub B, is QVB sine of theta. And again, it's, we're right now in part A, we're going to worry about the magnitude of this magnetic force first, right? So we're asking about the maximum magnetic force. So we want to find the maximum force. Well, if you look at this, Q, V, and B are all constants in this problem. How you make the force vary is the value of the sine of theta. Well, F sub B max equals QVB when sine theta takes on its max value, when sine theta equals 1, which occurs where theta equals 90 degrees. So when the velocity and the magnetic field are perpendicular to one another, that is when you have the maximum magnetic force, or the maximum magnetic force. Well, let's calculate it. So F sub B max is simply going to be QVB, 0.100 times 10 to the negative 6 coulombs. Break this out. I need more space. F sub B max, QVB, 0.100 times 10 to the negative 6 coulombs. V, 5.00 meters per second. B, 1.50 Tesla. F sub B max, when I do that calculation, is equal to 7.50 times 10 to the negative 7 newtons. Now, the question is, what direction should it be? Well, if we're talking about the maximum magnetic force, then we have to be talking about V and B being perpendicular, pretty much as I drew it. So if I go and I look at QV cross B again, well, again, we've done enough of these. If I say QV in my, if I say this, it's in a positive x hat direction, B cross B, B is going negative, that means it's going to be directly into the board, negative c hat direction. So, but, in general, F sub B max is mutually perpendicular to Q, to V and B. To be more specific, if I look at my diagram, let me look at my diagram now. Again, this is part B. If B is in positive x hat direction, and B is in negative y hat direction, as shown. And you could draw a different picture. I mean, as long as it, I mean, you could draw your picture with velocities going the other way if you want. I mean, as long as it's consistent. Then the force, the magnetic force, F sub B is in, so again, QB cross B, negative Z hat direction. As an example, again, in accordance with the right hand rule. So in accordance with the right hand rule, you want to be official about it. Okay, so again, that is how you would determine that. So it would be that magnitude, 7.50 times 10⁻⁷ newtons in the negative Z hat direction, in accordance with this diagram. You may have a different diagram than I do, but again, your diagram should be self-consistent. All right, let's look at OpenStax 22.9. That says, so a cosmic ray proton moving toward the Earth at 5.00 times 10 to the 7th meters per second experiences a magnetic force of 1.70 times 10 to the negative 16 newtons. What is the strength of the magnetic field? What is the strength of the magnetic field if there is a 45-degree angle between it and the proton's velocity? All right, and then B says, is the value obtained in part A consistent with the known strength of the Earth's magnetic field? at its surface. So this truly does happen. We have these cosmic protons that come in, and they get caught up in the Earth's magnetic field, and they spin around, they fly around. In fact, a lot of them fly around in spirals. So a cosmic ray proton moving toward the Earth at 5.00 times 10 to the 7th meters per second experiences a magnetic force of 1.70 times 10 to the negative 16 newtons. What is the strength of the magnetic field if there is a 45-degree angle between it and the proton's velocity? B, is the value obtained in part A consistent with the known strength of the Earth's magnetic field at its surface? Okay, so again, a lot of stuff there. I have to erase this for real estate purposes, so let's do it. So again, this is another application of the Lorentz force law. We're going to work on part A. All right, so all those words, what do we know? Well, we know V, and that is the speed of the proton. 5.00 times 10 to the 7th meters per second. That's the speed of the proton. Again, I'm just doing the magnitude. Q. We know the charge of the proton, right? It's positive E, or positive 1.60 times 10 to the negative 19 coulombs. Again, the charge that's important is a charge that's being affected by the magnetic field. Again, charge of proton. And F, magnitude of F is going to be 1.70 times 10 to the negative 16 newtons. And theta equals 45 degrees. That's the angle between V and B. We want to know what the magnitude of that magnetic field is. We don't know B. All right. So how do I figure this out? Well, I go to Lorentz force law. And I'm just going to talk about the magnitude right now. So again, the force, magnetic force, is going to be Q B cross B. And if I just take off the hats and worry about the magnitudes, the magnetic force F sub B is going to be Q B B sine of theta. I want to find B. So B will be F sub B over Q B sine of theta. Or B is 1.70 times 10 to the negative 16 newton divided by, let's see here, put all this together, 1.60 times 10 to the negative 19 coulombs times 5.00 times 10 to the 7th meters per second times the sine of 45. Put all that in there. All right. You do this, you find out that B, the magnitude, is going to be 3.01 times 10 to the negative 5 Tesla. Again, if you're using SI throughout the problem, and again, I use coulombs, meters per second, I use SI throughout the whole problem, and your answer should be in SI, should be in base SI. So in this particular case, your answer for the magnetic field strength should be in Tesla. So I have 3.01 times 10 to the negative 5 Tesla. Is that a reasonable magnetic field strength? So I'm going to keep that here, and then let's kind of let's talk about, is that reasonable? Well, for part B, Wikipedia, and there's a good source there. Wikipedia says that the Earth's Surface magnetic field. A little research. Is between, or ranges between 25 and 65 microteslas. Well, that to us is 2.5 times 10 to the negative 5 teslas. And it ranges from that all the way to 6.5 times 10 to the negative 5 teslas. And as you can see, our value, 3.0 and 10 to the negative 5, is right in that range. So yes, this is a reasonable value. The calculated B is in the range. So the answer would be yes. Again, don't just say yes with some backup. I mean, granted, Wikipedia research is not the bona fide be-all and end-all research, of course, but I mean, it's something, you know. So I mean, I did my effort, minimal effort to, you know, research magnetic field strengths at the surface of the Earth, and yeah, I believe that, and our answer is right in that range. So yeah, it is a reasonable value. All right. So now we have this concept of the magnetic force related to the magnetic field, and so now we're going to kind of look at some applications. All right, and so one of the behaviors that you will see, and let me kind of just bring out an application of this. Let's imagine here for a moment that I have a uniform magnetic field. Let me kind of just draw it out here. A little bit of a big picture. So I have a large uniform magnetic field. You see the tail feathers, and that they are all, that just basically means it's uniform, and in the negative z-hat directions, all into the board. So all this is really demonstrating here is that I have a uniform magnetic field, all into the board. And I'll tell you it's uniform. It's all perpendicular. And I'll draw another row. All right. Now, what happens if I put an electron in this magnetic field? So again, this is a uniform magnetic field. Okay. Now I'm going to have an electron come in here, and I'm just going to have the initial velocity of this electron be straight up in the board. So we're going to say, I'm going to imagine my electron, and it's going to be initially, I'm going to put it right here, and actually I'll stick it right here. I'll stick it right here, and it's going to be straight up. Again, this is an electron. All right, so you have an electron here, and the velocity, this is a velocity. So the velocity is straight up. Now, what is the force that's going to be on that electron? Well, again, Lorentz force law, right? So I look at the force and say, well, the force is going to be Q B cross B. All right, so V is straight up. I cross it with B, which is into the board. So that you would think the force, you know, the V cross B would be directly straight out. But remember, the electron is a negative charge. You flip the sign, it is straight in. So what's happening here is that when the velocity is oriented this way, my force is going to be straight inward. it's actually going to be pulling on the electron to go to the right. Now, the force is perpendicular to the velocity. What's that going to do? Well, it's going to cause the electron to deflect a little bit to the right. And in fact, we will notice that the electron will actually deflect in a circular path. Let's say later on, I'm up here. And I say, where's the electron? And now it's going at a velocity to the right. What's the force going to be? Again, QV cross B. You think it would be up, but then the electron is negative, flips it to be straight down. Straight down. And what you're going to see is it's going to undergo a circular path, and it's going to undergo what's called uniform circular motion, the same uniform circular motion we studied in Physics 1. Because I keep on pulling on it, and now it ends up over here. And its velocity will be again straight down. And again, if I go off and I say, okay, well, QV cross B, you would think it'd be going to the right, but no, it's you flip it because it's a negative charge. You go to the left. So again, it's still going to be going at that same magnetic force. And finally, let's say we take a spot down here at the bottom. An electron is heading out to the left now. So what's that direction going to be? Well, here we go. Let's see. QV cross B. Well, you think that my thumb would be going down, but it's actually flipped to go up. So what I have done is I have a nice, beautiful circle. The electron is moving around in a circle in what's called uniform circular motion. It's moving in a circular path. So in this arrangement, the electron, the magnetic force, F equals QV cross B, forces the electron to move in a circle and undergo uniform circular motion, just like we talked about in chapter 1. So again, there's all, what we talked about in chapter 1 is always, we always can go back to chapter 1. That's all, physics is by its very, very, very nature comprehensive, uniform circular motion. In fact, this is one of the experiments that J.J. Thomson did to help explain that the electron was a negative charge. He would force a beam into a magnetic field, and I've done this in the laboratory myself. You did this in your sophomore physics class. It's a very beautiful experiment. The beam undergoes a beautiful, perfect circle. And that is one way of proving in this kind of orientation that the electron is whatever the beam is made out of, it is a beam of negatively charged particles. Electron is a negatively charged particle. So again, J.J. Thomson did this very experiment. All right, so what I've just shown you here is that, well, I have shown you that, well, given that B is perpendicular to B, so we know that the force on the electron is going to be QB cross B, right? Since B is perpendicular to B, then we can write that the force, we can just say the magnetic force, little B here for magnetic, is simply going to be QVB. Because sine 90 degrees is 1. However, the electron undergoes uniform circular motion. So according to Newton's second law, it feels a centripetal force. And remember, the centripetal force is the right-hand side of Newton's second law. It is an inertial force. It is when you do Newton's second law and polar coordinates. So we would literally say that the magnetic force equals the centripetal force. The sum of all forces, mass times acceleration. The mass times acceleration part is the right-hand side. The centripetal force is the right-hand side of Newton's second law. So we would literally write that QVB is mv squared over r. R is the radius of that circle. All right, and so essentially one of the v's cancels out, and we literally can figure out the radius of the circle. The radius of that circle is going to be mv over qb. Radius of circle of electron path. So the beauty here is that J.J. Thomson was able to solve, he was able to measure that radius. He's able to control B, and he was able to understand V. He could measure V, and he was able to get a charge to mass ratio. Now, the problem is at that time, they did not know the charge, they did not know the mass. All you could actually do is calculate the charge to mass ratio. It took the work of Robert Millikan, American physicist Robert Millikan, to actually determine the actual mass of the electron. I'm sorry, the charge of the electron. I apologize. Robert A. Millikan was able to determine the charge of the electron, and then once Thomson knew that information, he was able to determine the mass of the electron. But the best that Thomson can do with this experiment is determine a charge to mass ratio. Okay, and so we see that we will see a lot of examples that high-speed charged particles, like in cosmic rays, get into the Earth's magnetic field and actually start spiraling. And so, and this is something that you see, you see like in the auroras, aurora borealis, aurora australis. You see this, you see the charged particles, getting accelerated and actually ionizing the air and creating these beautiful colors that you'll see if you live, further north, and we're able to see this. All right, and so charged particles get trapped in the Earth's magnetic field. The Earth is basically a magnet. So you have these charged particles. So you see examples of this. Charged particles from cosmic rays get trapped in the Earth's magnetic field. And start spiraling. Now, if we look at the Earth, again, the North Pole is really the South Pole, South magnetic pole, and what we call the South Pole is really the North magnetic pole. So we have things screwed up, right? So, but we look at it and we see, okay, well, the magnetic field lines are going to be strongest at the poles. So come around, re-enter. You see that they're more spread out in the lobes, but they're strongest at the poles. So these particles spiral in, and the magnetic field at the poles has become stronger, and they start spiraling in to the point where they actually ionize. So the charged particles spiral along the magnetic field lines, which are much more concentrated. So again, these magnetic fields go like this, right? Because they go south to north. Much more concentrated. At the poles. The more they gain enough energy to ionize gas, ionize the air, and create the auroras. It's the aurorae. All right, and so that's what we see. If we live further north, we would see the beautiful northern lights. We would see when these charged particles and cosmic rays come in, we'd see beautiful arrays of arrangements of greens and blues and red lights and orange lights. I mean, we would see the the ionization of the gas, and they'd be giving off electromagnetic radiation. And if you look further, very, very far south, like maybe in Australia, you'd see the aurora australis. Here we see the aurora borealis in the north, the aurora australis in the south. And there's just because the charged particles are getting trapped in the magnetic field of the Earth. All right. There's another example of these charged particles getting trapped in the greater magnetic field of the Earth. We have charged particles that get trapped in what's called a Van Allen belt. Let me explain that here a moment. Let me give you a picture. I can't do justice with my drawing abilities, so let me show you a picture here. Give me a moment. And so, it turns out that charged particles have been trapped in the Van Allen belt for a long, long time. And what you end up seeing is you see a very large amount of radiation, a dangerous amount, in fact. And so let me get to that picture here. Give me a moment. All right, getting close. Here we go. Not yet. It's a nice picture of the Van Allen belt. Let me share my screen here. All right, so on the screen, you'll see a picture of these bands called the Van Allen belt. All right, and so so they're named after astrophysicist James A. Van Allen. He discovered these, and essentially what it is, these belts are are essentially trapped cosmic rays that are trapped in the Earth's magnetic field. And in fact, the radiation is extremely intense. You want to avoid any kind of space flights going through these Van Allen belts. And in fact, if the devices on your spacecraft happen to have any kind of delicate instrumentation, electronic instrumentation, you definitely want to keep them away from the Van Allen belt. So for instance, to give you an example, I mean, the astronauts that landed on the moon, they went through the Van Allen belt in a few minutes. But in that few minutes, they received more radiation dosage than radiation workers should receive. So basically twice the amount of radiation dosage that radiation workers who should receive annually, just in a few minutes that they pass through the Van Allen belts. So when you have any kind of space flight, you want to make sure that you very much avoid the Van Allen belts. So again, that is nothing more than this concept of trapping these particles. Now the Earth has a magnetic field. So you see the Earth magnetic field, the Earth magnetic field has these radiation belts, and that's just a little Earth. Jupiter has much more intense radiation. In fact, you know, if you go on the you know, it has, you know, the four main moons, Io, Europa, Ganymede, and Callisto. The closest moon is Io. That's the one that's also extremely volcanically active. In fact, it is the most volcanically active object in the entire solar system. It actually repaves itself about every couple of years. It has lava that is hotter than the lava we've experienced on Earth in the last about 3 billion years. It is extremely volcanically active. Io, the magnetic fields on Io are so intense you wouldn't be able to stand it, and that's because of it's being bombarded with Jupiter. Another, you know, when you were talking about is there life on Europa, you know, Europa actually is covered in a very thick ice, and there are oceans about as big as the oceans on Earth. I mean, these jovial moons are very large, and so Europa definitely has subterranean oceans. And it is believed right now that so does Ganymede and Callisto. So if there's any kind of hope for life in the universe, I mean, there's an interplay between because Jupiter's gravity is so strong, it's constantly squeezing, rarefying and squeezing back and forth these planets. So much so that it has enough energy to keep a liquid ocean. But at the same time, Europa is very far away from the sun, so it has this thick ice. And so the ice can actually protect against these magnetic fields. So if there is kind of life in there, you would have some protection against these very strong magnetic fields from Jupiter. But again, Jupiter has a great magnetic a great magnet, much greater than that of Earth. All right, and so again, that's a result of the effect that magnetism or magnetic fields have on charged particles. Okay, let's look at some problems. Stop sharing here. All right, I'm going to look at OpenStax 22.12. OpenStax 22.12. A cosmic ray electron moves at 7.5 to 10 to 6 meters per second. Perpendicular to the Earth's magnetic field. an altitude where the field strength is 1.00 times 10 to the negative 5 Tesla. What is the radius of the circular path the electron follows? So very similar to the example I just drew. All right. A cosmic ray electron moves at 7.50 times 10 to the 6 meters per second perpendicular to the Earth's magnetic field at an altitude where the field strength is 1.00 times 10 to the negative 5 Tesla. What is the radius of the circular path the electron follows? So again, you have an electron in a perpendicular magnetic field, just like the picture that I drew. All right. So again, I'm going to erase the words here. All right. V is going to be 7.50 times 10 to the 6 meters per second. What is that? That's the velocity of the cosmic ray electron perpendicular to the Earth's magnetic field. All right, let's see. B is 1.00 times 10 to the negative 5 Tesla. Again, that's the Earth's magnetic field strength at this location. And we're also told that V is perpendicular to B. So again, we're setting up essentially the problem that we had that I drew earlier, where we have an electron going around in a magnetic field. And so it's going to go in a circle. So again, we know that, we write down our equation. Again, we know that, the force, the magnetic, kind of remind you here, if the magnetic force is QV cross B. Remind ourselves what we're doing again. So magnetic force is again QV cross B. Okay, and if V is perpendicular to B, let's worry about the magnitude now. So magnetic force will be QV B sine of 90 degrees. 90 degrees, sine 90 degrees is 1. That means that the magnetic force is QVB, but again, we know that the electron is going to move in a circle. So the electron moves in a circle, with uniform circular motion at speed v, orbital speed v, and radius r. So it's got to has to balance out with the centripetal force, mv squared over r, just like in physics 1. And so again, one of the v's cancels out. And so we know, again, that the radius, solving for it, is qb over, mv over qb. mv over qb. All right, so we want the radius of that path. Okay, that's our equation. Let me erase this stuff and we'll just write this equation down. So again, R is mv over qb. R, the mass of an electron. You have to look this up, but the mass of an electron is 9.11 times 10 to the negative 31 kilograms. The velocity we're told is 7.50 times 10 to the 6 meter per second. And it's divided, the electron charge, I'm just going to use I know it's negative, I'm just going to use the magnitude of it. Electron charge is going to be 1.60. It's a fundamental electron charge, 1.60 times 10 to the negative 19 coulombs. And the magnetic field, I'm told at this particular location from the Earth is 1.00 times 10 to the negative 5th Tesla. I worked that out. I find out that the radius of the circular path that the electron is going to follow will be 4.27 meters. Electron is going to go around a circle, and a circle of radius 4.27 meters. Because of its interaction with the Earth's magnetic field. Okay, look at OpenStax 22.14. That one says, A, viewers of Star Trek hear of an antimatter device, or sorry, antimatter drive. The viewers of Star Trek hear of an antimatter drive on the Starship Enterprise. Okay. One possibility of such a futuristic energy source is to store antimatter charged particles. in a vacuum chamber. Circulating in a magnetic field. And then extract them as needed. Antimatter annihilates with normal matter. Producing pure energy. What strength magnetic field is needed to hold antiprotons? Moving at 5.00 times 10 to the 7 meters per second. In a circular path of 2.00 meter in radius. I'm running out of space here. All right. I'll read the rest of it in a moment here. So, A, viewers of Star Trek hear of an antimatter drive on Starship Enterprise. One possibility of such a futuristic energy source is to store antimatter charged particles in a vacuum chamber, circulating in a magnetic field, and then extract them as needed. Antimatter annihilates with normal matter, producing pure energy. What strength magnetic field is needed to hold antiprotons, moving at 5.00 times 10 to the 7 meters per second in a circular path of a 2.00 meters in radius? Antiprotons, this is what I am not writing down. Antiprotons have the same mass as protons, but the opposite or negative charge. Okay, so antimatter, it looks like the twin of matter, except the charge is opposite. Okay, so we know the protons have a positive charge. Antiprotons would then have a negative charge. It's antimatter. And then B, part B is this field strength obtainable with today's technology, or is it a futuristic possibility? All right, so a lot of words, problems not so bad. So again, we're looking at something that may be science fiction, but maybe it can actually be real science. All right, and we're kind of seeing it, you look back in the days of watching Star Trek back in the 1970s, if you've ever watched those. I mean, a lot of the things that you see on Star Trek actually are, like the automatic doors, electron beams, everything else. Those are all real. I mean, we see doors opening for us. So a lot of these things, they end up becoming reality. So the question really is, we want to know if we can, what is that magnetic field that's needed? And we want to circulate antiproton. So the mass of an antiproton, the mass of a proton is 1.66 times 10 to the negative 27 kilograms. Again, that's the mass of antiproton, which is the same as the mass of a proton. All right. The velocity of these antiprotons is 5.00777 meters per second, as we said. 5.00777 meters per second. That's the speed of the antiproton. All right. We're also told that the radius of the circular path will be 2.00 meters. So that's the radius of circular path, and they have to be negative in order to have the spinning effect, because you have to switch, you have to flip the sign, right? So the radius of circular path of antiproton. So using the same math as before, so essentially, what problem did we do before was OpenStax 22.12. So using the same math, as OpenStax 22.12, again, same math that we did before. Again, we find out that the radius is mv over qb. It's the exact same problem. We don't have electrons, we have another negative particle called the antiproton. All right, and so we want to solve for the magnetic field. So simple matter of doing that, you just switch between B and R, and you get B is mv over QR. All right, and so the magnetic field, working this out, the mass of a proton is 1.66 times 10 to the negative 27 kilograms. V, we're told, is the 5.00 times 10 to 7 meters per second. And then QR. Q, charge of a proton. Again, it's a fundamental electron charge. Fundamental electric charge, 1.60 times 10 to the negative 19 coulombs. And R, 2 meters. 2.00 meters. That's what our design characteristics are. When we do all of this, we find out that the magnetic field required will be 0.259 Tesla. And to answer part B, this magnetic field is easily obtainable. In today's technology, no doubt about it. It's an easy field. You can get many Teslas. So you could do this now. You can create this antimatter drive with this particular design. This Star Trek technology can be done in with today's capabilities. All right. The next topic I like to discuss is, when we talk about how magnetic field affects electrons or charged particles, what about charged particles inside of a conductor? And so let's look at that. That's also a very important application. So let's take a look at the effect of magnetic fields and charged particles contained in a conductor, or I should say on the surface of a conductor. All right. So we study what is called the Hall effect. I mean, really, it is a study This is the effect of a magnetic field on charges in a conductor. All right, and so this actually is very important. It's a very important application, and as I will show, it'll actually be another way of showing you what is a sign of the charges in a conductor. And this is one way of determining that the charges in a conductor truly were electrons. And you know, we can also show that the charges in some semiconductors are proton, or not proton, but positive charges. And so you can do this with this experiment. This experiment was devised by Edwin Hall. Give you some history. Edwin Hall, he's an American physicist. And he lived between, he discovered this. So the Hall effect was discovered by him in 1879, which consequently is the same year that Albert Einstein was born. So again, 1879 is a very important year. So 1879 is when the Hall effect experiment was performed, and again, you see another American. We've already talked about our first American physicist, you know, that has come onto the stage. That's Benjamin Franklin. Now we have Edwin Hall. All right, and so Edwin Hall, this is a very important discovery. So let's see what it is that Edwin Hall did. All right, and so we're going to look at, let's kind of look at a couple of different cases. And this is going to kind of take us back to our chapter 20 studies. And that is, let's take a look at a conductor. And so first of all, we're going to look at a conductor, a strip, conducting strip, that's going to contain negative charges. So we're going to have a conducting strip actually, let's do, we'll do negative charges. And see what happens. All right, so again, negative. So what's going to happen here is that we're going to put this in a magnetic field. All right, so we have a magnetic field that's going to be coming out of the board. So again, I'll draw these little circles with dots. That shows that, again, these dots represent like the heads of an arrow. You know, the X's would represent the tail feathers if the arrow is going away from you. So this is a magnetic field. So again, we have a strip in a magnetic field. It's a conducting strip. And in here, we have electrons that are going to go, let's say I have an electron. I'll give an example of it. Here's an electron, E minus, and it's going to have, let's say, a velocity to the left. All right, so we'll kind of erase one of these guys here. It's going to have a velocity to the left. All right. And of course, what that means is that the current always flows to the opposite direction of the electron. Remember, a current is either the flow of where positive charges will flow in the positive direction or negative charges in the negative direction. Again, negative times negative is the positive. So the current is going to be positive in each case. So in this particular case, the current would be to the right. The actual velocity of the electron is to the left. And the magnetic field is out of the board. Again, so again, now the question comes down to is like, well, what kind of forces is the electron going to feel? I mean, again, if you're talking about negative charged particles in a magnetic field like this, what force would it feel? Well, what do? Well, you apply Lorentz force law. So F sub B is QB cross B. Okay, so, well, V is doing what? So again, my V, my hand would go to the, to the left, and I'm going to cross it with B. My B is going out, right? So my hand moves to the left because velocity, again, V comes first. Hand goes to the left. My fingers, again, my fingers initially point to the left, and I cross it with the magnetic field. The magnetic field is out of the board. It's gonna come toward you. Where does my thumb point? Again, V cross B. My thumb points up, but we're talking about negative charges, so we have to flip it to down. So again, the magnetic force on these charges will be downward. So the magnetic force on the negative charges will be downward. So negative charges, say electrons, parentheses electrons, will be downward. All right, so what I'm going to see essentially is a collection of negative charge. I'm going to see a separation of charge. So I'm going to see the bottom of the strip becoming more negative. Negative charges will collect on the bottom of the strip because they're being pushed down by the magnetic force, leaving the top of the strip to become positive. And what does that do? Well, I have a separation of charge. That means there's going to be a potential difference, epsilon, from the top of the strip to the bottom of the strip. They're going to be a different potential. So there'll be a potential difference, epsilon. So epsilon is the potential difference. Between top and bottom of the conducting strip. All right, so Paul discovered this. And again, this is a lab that I've done myself in my sophomore year in physics. Again, it's one of those labs that, one of the beauties about being a physics major, when you're a sophomore, your second year in physics, you get to work all these labs out. All the famous quantum mechanics labs, this lab, the Hall effect, all these you get to work out in your sophomore year. All right, so again, epsilon, we'll see that there is a collection of negative charges on the bottom of the strip and a collection of positive charges on the top of the strip, and there'll be a potential difference, epsilon. What happens now if I happen to have this strip have positive charges in it? What happens now? Again, this is an example of a strip of negative charges. What happens if I have a strip with positive charges? Let's make my same strip. Let's say, for instance, it's made out, instead of made out of a conductor, it's made out of a semiconductor, for instance. So now we're going to have a strip with positive charge carriers. So we're going to still say that the current is going to be going to the right. Now this time, again, I still have the same magnetic field. And I'm just going to, I'm leaving a space so I can write stuff down about my electron, or my charge. Now I have a charge that is positive. Okay, what's it going to do? Well, the positive charge, again, is going to flow. Again, it is, when you have a current going to the right, if it's positive charge, it's going to flow to the right, right? Positive charge flowing to the right gives you, is the same as gives you the same current as a negative charge flowing to the left or flowing in the negative direction. So now my positive, whatever my positive charge is, it's going to now have a velocity moving to the right. Now, if we look at QV cross B, what's going to happen? Remember, what's being moved are positive charges. Okay, now if I do QV cross B, and whatever my charges are, if they're positive, well, what's going to happen now? Well, again, in the last case, what charges are being pushed? The negative charges. They're being pushed down. So the charges that were being pushed were the negative charges. So of course, the negative charges are going to collect in the bottom because they're being pushed down. The charges being pushed now, in this particular example, the positive charge carriers are positive charges. Where are they going to be pushed? Well, let's see. I line my fingers up. QV. Where's the magnetic field? It's out of the board. So again, it's going to be QV cross B. My thumb is down. QV, or V, to the right, cross B, because it's out of the board. Thumb is down. There's no flipping going on because the charges are positive. So that means that the positive charges are being pushed down. QV cross B. The charges are being pushed down. What's being pushed down? Positive charges. So that means I'll have a collection of positive charges down here, leaving the top strip now to be negative. And again, there'll be another epsilon, but now the epsilon will be, the voltage will be the opposite polarity. And I know the polarity of the voltage from the top and bottom. I can actually then understand what is the charge of the charge carriers. I can use the Hall effect to determine that the charge carriers in a conductor are negative, and the charge carriers in, say, a semiconductor, many semiconductors are positive. And I can determine that by knowing the polarity of my voltage. Right? This is called the Hall EMF. All right. So the Hall EMF, as you can see, has opposite polarity. So epsilon that we just got done computing is what's called the Hall EMF. The Hall EMF for negative charge carriers, so the Hall EMF epsilon for negative charge carriers has opposite polarity. Than it does for positive charge carriers. The Hall effect can be used to determine the sign of the charge carriers. The sign, positive or negative, i.e., of the charge carriers. All right. All right, so that is the point of the Hall effect. Now, the question then comes down, well, can I actually compute this Hall voltage? Can I do that? So the question, well, how would I go about doing that? Well, the way to do this is kind of take a look at the initial problem again. Let's look at the case of the electron. How would I compute the Hall voltage? Right. So that's what's going on. So going back to the original picture, here's my strip again, and I'm just gonna kind of not draw as many understand that it is inundated in magnetic field. So again, the magnetic field again is totally into the board everywhere. We understand that. All right, so I'll kind of put some field lines in, but understand that the magnetic field is everywhere into the board. I'll put a few of them in here, just kind of remind us that it's into the board. That's a magnetic field. Again, same experiment, but I need a little bit more space to kind of draw some stuff. So let's look at my electron. Okay, we know the electron is going to have, let's say, a velocity going to the left. And it's going to push negative charges toward the bottom of the strip, leaving the top of the strip positively charged. But this can't go on forever. I mean, every single time, once you have this charge separation, now you have an electric field that's going to oppose it. All right, and so again, the Hall effect. So the magnetic field will push negative charges to the bottom of the strip. To the bottom of the conducting strip. Leaving the top of the strip positive. But the separation of charge creates an electric field that opposes it. All right, so because you have the separation of charge, right? It's kind of like the parallel plate, parallel plate arrangement where you have, again, so what's going to happen here? Well, the electron is going to feel what? A negative charge pushing it down. Call that F sub B, right? The magnetic field. But what's the electric field going to be? Well, where is the electric field going to be? Well, because you have this this collection of charges on the top. Remember, electric field always goes from positive to negative, right? It starts on a positive charge and it terminates on a negative charge. Now you have these electric field lines forming. Right? And now what's going to happen? Well, the electric field lines are going to go from top to bottom. Now, so if the charge was positive, it would be pushed down by the electric field lines. However, the charge is negative. It's going to be attracted upward by the electric field lines. So this electric field lines are going to cause an electric force pulling up. All right, so the electron is going to feel an electric force pulling it up and a magnetic force pulling it down. This process of charge separation will continue until those forces balance. So the process so again, the electric field will be downward causing an upward electric force on an electron. All right. The charge separation process continues until these forces are balanced. Force electric, or let's see here, force electric equals force magnetic. When that happens, the process stops because at this point, there is no charge on the electron. The electron at that point, once it's balanced, the electron does no longer feels a net force. The total force on any given electron at that point will be zero, and they will no longer have any reason to separate. There will be no electrons being pushed down anymore. You have had the maximum charge separation. So when you have the maximum charge separation, electric field on any given electron, any given charge carrier will be balanced by the magnetic field, and that electron will not feel a net force. All right. So when you have this force, so again, what's happening? Magnetic field B will push negative charge to the bottom of the conducting strip, leaving the top of the top of the strip positive. Sorry. All right. So again, the magnetic field B will push the negative charges to the bottom of the conducting strip, leaving the top of the strip positive. But this separation charge creates an electric field E that opposes it. Electric field will be going downward, which means because the charge is negative, it's going to experience electric force upward. And this process will continue until the electric force and the magnetic force are balanced. And then after that point, the electron will feel zero net force, and the Hall effect will stop. All right. And so again, at this point, once you see balance occur, all right. So I'll erase my picture. So when the electron, when a general electron feels a balance between the upward electric force and the downward magnetic force, it feels no net force. And the Hall effect is complete. So you'll find, again, at this point, at the balancing point, again, you'll find out that the electric force balances the magnetic force. F sub E equals F sub B. What is F sub B on a test charge? It's QE. And I know where the directions of the forces are, so I'm not going to worry about directions. I know E is up, electric force is up, and the magnetic force is down. And what's the force? Given that everything is perpendicular, it's QVB. Again, we know that V is perpendicular to B. Q's cancel, which means I can write that in this case that the electric field E is nothing more than VB. All right. Now, remember, this is like the charged plates, the separated charged plates. There is, so let the width of the strip be L. So again, here's my strip. Again, remember we have the magnetic field going out of the board. That's the magnetic field. And let's draw a couple others in here to remind ourselves that it's in the strip as well. We also know that here's your electron, and its velocity is straight down the strip. Its electric force is up. And its magnetic force is down. All right, and this is my electron. All right, so we're gonna say, we know that we have an epsilon potential difference across. Let's just say that physically the strip has a width L. Okay, that's the width of the strip, has a width L. What do we know about, remember back in the parallel plate arrangement, we know that epsilon, remember V equals ED, epsilon is going to equal EL, right? So again, we have two charged conductors. With a separation that are parallel. With a separation L. All right. So what I can then do is, if I know that epsilon, the EMF is equal to EL, I can then solve for E and substitute it. So instead of E, I can write epsilon over L. So I can write in here that epsilon over L is VB. Or I can write the Hall EMF as BLV. Hall EMF. BLV. All right. And so if I know the magnetic field, if it's totally on the board perpendicular to the velocity V, and the strip has a width L, I can then calculate the voltage. In fact, this is a way of figuring out the drift velocity of the electrons. You could do it this way too. Experimentally, you can figure out the Hall voltage divided by the magnetic field and the strip width, and you can get what the actual velocity of these charged particles are. And then that's another way. We talked about drift velocity back in chapter 20. Well, that's one way of experimentally doing it. You can actually use a Hall effect to find the drift velocity. So V, remember, will be the drift velocity. You can actually experimentally measure this, and you can show that it's in millimeters or a fraction of a millimeter per second. So again, that's one way of another application. Again, one application of the Hall effect is determine what is the sign of the charges in the first place. Within what are the sign of the charge carriers? But another application of the Hall effect is to determine what is the actual drift velocity. You can figure that out too. Yeah, I think this. See this? All right. I want to write this darker ink here, just to make sure it's a very important result. Epsilon B L V. All right, Hall EMF. So let's work a problem with the Hall effect. I'm going to look at OpenStax 22.24. All right, OpenStax 22.24. That says A. What is the speed of a supersonic aircraft? With a 17.0 meter wingspan. If it experiences a 1.60 volt Hall voltage, between its wingtips, when it is in level flight, over the North Magnetic Pole. Where the Earth's field strength is 8.00 times 10 to the negative 5 Tesla. B, explain why very little current flowed. As a result of this Hall voltage. Of this Hall voltage. All right. All right, so 22.24a, open stacks. A, what is the speed of a supersonic aircraft with a 17.0 meter wingspan if it experiences a 1.60 volt Hall voltage between its wingtips when it is in level flight over the north magnetic pole where the Earth's field strength is 8.00 times 10 to the -5 Tesla? B, explain why very little current flows as a result of this Hall voltage. All right, so what on earth are they talking about? So we have a very fast aircraft. All right, so let's kind of, again, definitely a problem to draw a picture. All right, so we have a very fast aircraft. Let me erase these words. All right, looking at part A. So drawing a picture, I don't draw very well, but here's my airplane. The airplane is going to have a large velocity. You imagine the wingtips kind of pointing out. I'll do the best I can. But the idea is the wingtips, well, let me redraw this. All right. Airplane. And my velocity to the left here in my drawing. And imagine that the wingtips are going to come out. You know, they're kind of think of it on the side of the plane. There's a length L from tip to tip. Okay, we have a length L. We're imagining there's going to be a Hall voltage epsilon across the wingtips. All right, and there's a magnetic field down, perpendicular to the velocity. All right, so we have ourselves a situation where we have this object, you know, that's essentially, essentially a conductor. You know, it's made out of metal. It's moving very quickly to the left, and it experiences. I mean, again, it's charged. A bunch of charge carriers moving very fast to the left in a magnetic field. And so the idea is, well, what is going to be the Hall voltage you experience? You would experience a potential difference across the wingtips, which would possibly drive a current. So what would we actually have here? Well, again, the wingtip, the wingspan, L is 17.0 meters in this aircraft. Epsilon, we're told we measured the Hall voltage of 1.60 volts. Okay, so it's a Hall voltage from wingtip to wingtip. The magnetic field of the Earth, again, it's because the Earth has a magnetic field. So it's 8.00 times 10 to the -5 Tesla. And so, again, the Hall voltage, we just derived it. Epsilon is BLV. Deriving the Hall voltage as we just did. We want to find V. We solve for V. We find that it is going to be epsilon over BL, or the 1.60 volts divided by the 8.00 times 10 to the -5 Tesla divided by the wingtip length of 17.0 meters. We find out that the velocity of this aircraft will be 1,176 meters per second. Very fast supersonic aircraft. All right, so there you have it. So that's the velocity. So you definitely have a Hall voltage. Now, part B asks, explain why there's very little current flow as a result of this Hall voltage. So I'm going to erase this, and I'll write you a little something of the current flow. All right, so there you have it. Basic calculation utilized in the Hall equation, the Hall EMF equation that we derived earlier. Part B says, so once established, and this is why I wrote it, once established, the Hall voltage would push charges one direction. I mean, we kind of talked about this already. The Hall voltage would push charges one direction. And the magnetic force acts in the opposite direction. Oh, I'm sorry. Due to the magnetic force, sorry, I wrote. The electric force pushes the charges in the opposite direction. Once the electric force and magnetic force is balanced, on a given charged particle, it will experience no net force. It will experience no net force. Causing its motion. And current, due to the Hall effect, would stop. We'll say cease. Okay, so what I wrote down then essentially is, once established, a Hall voltage would push charges one direction due to the magnetic force. The electric force pushes the charges in the opposite direction. Once electric force and the magnetic force is balanced on a given charged particle. So once the electric and magnetic forces are balanced, we'll say. Sorry about that. On a given charged particle, it will experience no net force causing its motion, and current due to the Hall effect would cease. So essentially, this whole concept that that the magnetic force, electric force balance out is the reason why you're not going to get a large current across the wingtips, because of the Hall effect.